Hello, everyone on the phone, and welcome to this World Economic Forum Young Global Leaders Circular Economy Speaker Series session. My name is Wesley Spindler. I'm a member of the Young Global Leaders Circulars program, as well as an Accenture strategy consultant. So today, we're lucky enough to be joined by Dr. Jennifer Holmgren, the CEO of LanzaTech, who will be speaking to us on the topic of creating a carbon-smart future. Now, prior to kicking off the session, I just wanted to cover a few housekeeping items. So firstly, on entry, all participants will automatically be muted to eliminate the background noise during Jennifer's presentation. If you do wish to be unmuted at any point, please send a message via the chat function to the host of the session, which is listed as Quentin Drool. And the chat function is located at the top right-hand side of the WebEx window. Additionally, there will be time for questions at the end of Jennifer's presentation. If you would like to ask a question, again, please send through your questions through the chat function to the host, which is listed as Quentin Drool, and that's actually my colleague, Dan. And finally, the session will be recorded and available following a few days following the session on YouTube and on www.thecirculars.org. With that said, I would like to welcome Peter Lacey, who is the Global Managing Director within Accenture Strategy and Sustainability Practice. Peter, over to you to open the session.
Thank you very much, Wesley, and welcome to everybody who is on the call, and in particular, a big welcome to Jennifer, and thank you for making time today. We're very excited to be, I think, re-energizing the speaker series. Excited that we can actually, in particular, I think, use the speaker series going forward to showcase some of the extraordinary innovation that we've seen through the circulars. And we've got a phenomenal group of speakers lined up over the next 6 months to do exactly that. So let me introduce Jennifer to all of you. She's the Chief Executive of LanzaTech and LanzaTech Inc. and has been since June 2010. Jennifer has over 20 years of experience in the energy sector and a proven track record in the development and commercialization of fuels and chemical technologies. I think the interesting thing for me is that LanzaTech recognized the chance to transform waste carbon into an opportunity, and that really is, I think, revolutionary thinking with enormous potential, and it was what led to the company winning the World Economic Forum's Young Global Leaders Award for Circular Economy Entrepreneur at the Circulars in Davos in 2016. I think this thinking has accelerated the reduction of harmful emissions while creating new economic opportunities for companies, for communities, and countries around the world. Jennifer has a stellar career that precedes her time at LanzaTech, and we're really looking forward to you, Jennifer, walking us through some of your journey, where you are and what you see in the future. And then once we've had a chance to listen to you up front, Wes and I will moderate a Q&A discussion. So for those of you who want to ask questions, feel free to post them in the online chat function, and also we will try and put those to Jennifer in at the end of the presentation. So Jennifer, without further ado, thank you very much for making time and welcome.
Thank you. Thank you very much. It's really an honor to have the opportunity to speak to you, and I'm especially excited to be part of this growing movement to think about our resources in a circular fashion so that we can that can really sustain the 9 billion people that we're on a path to. So let me tell you a little bit about what we do and why we do it. And we say that what we're doing is we're working a carbon smart future. As context and to share how we think, let me show you our first slide. By the way, I no longer have control. I'm not able to flip my slides. I got it. Here we go. Okay. First slide is just a picture of the Easter Parade in New York in 1900. And what that circle is showing you is the only car, the only automobile there. Everybody else is in a horse and buggy. Now, the next slide is 1913, just 13 years later, again, Easter Parade, New York, and you can see it's all cars. There is no buggy. In 13 years, there was a complete transformation from a world of horses to a world of autos. And the next slide is simply my favorite quote on disruption. As Henry Ford says, if we'd asked people what they wanted, they would have wanted a faster horse. And so the reason that we're here is to talk about approaches that can disrupt our carbon economy. The world desperately needs a different way to think about carbon. Today, if you look at the next slide, you'll see that it's always a one-way approach. We start with a fossil resource and we either make our chemicals or make our fuels or we power our plants. And from that either comes waste that we dump into a landfill or that goes into an emission that someday we hope to be needing to sequester. And that path puts us in we make money when we make the products, but then we use money when we have to get rid of them or dispose of them. And so the world that we want to head to is one where these are not liabilities that need money to be disposed of, but rather they're opportunities. They become opportunity feedstocks. And that is really what we call a carbon smart world. A world where not all of the carbon that goes into our products is new. It doesn't all have to be new carbon coming from a fossil resource, but rather a world where carbon, these waste emissions can be recycled in some way, giving carbon a second life and allowing us to make money by creating products and also allowing us to do what we really need to do, which is reduce our new fossil carbon sources so that we can keep carbon in the ground, so that we can meet our COP21 commitments of staying within the 2 carbon budget. And so this really is what we are trying to do. And what LanzaTech does is exactly that. We are carbon recyclers. What we do is we take carbon emissions from, for example, a steel industry or other industrial sites. We take that carbon and biologically convert that emission into products like ethanol. And so let's just take a step back. You're used to the fermentation of sugar. You're used to a yeast molecule being used to take a sugar molecule and converting that to ethanol, which either ends up in your car or ends up in your beer. What we do instead is we have an organism that captures carbon and energy not from a sugar molecule, but from a carbon monoxide molecule. That is absolutely the only thing it needs. And it takes that carbon monoxide molecule and it converts to either ethanol or to a chemical. We do this in a continuous bioreactor. I come from the refining industry, and we use a lot of continuous processes. Most sugar fermentation is a batch process. And so this is much more like a refinery. What you are looking at the picture below the schematic is actually our 100,000 gallon per year demonstration facility at a steel mill in Hebei province. And they're literally, the steel mill waste gas comes into our fermenter and we produce ethanol. On the right, you will see a plot. This is a 50-day run at that specific demonstration site where we exceeded the ethanol productivity as well as the carbon uptake, the carbon monoxide uptake. To me, what is most exciting about this plot, though, is not that we exceeded the parameters, but rather that despite mechanical problems, we were able to get back on track after, say, a compressor shutdown and get right back to producing at the rates that we started with. This is actually really important because what you want to be able to commercialize a process or to really have industrial biotechnology, what you want is the ability not to have to shut down every time you have a mechanical problem. This is true in refineries today. You just can't stop operating while you fix a piece of equipment. And therefore, to me, this was the first run where I really understood that our process was ready for prime time and that this organism wasn't just a lab prima donna and that we were able to commercialize the technology. If you look on the next slide, you ask yourself, what kind of an organism can actually eat a waste gas stream that is full of contaminants? And the answer is, once upon a time, our planet was full of the same nasty gases. And there were organisms that lived at that time, in particular bacteria, that were able to eat this waste carbon monoxide, carbon dioxide, methane, and hydrogen that was in the atmosphere and metabolize that to products. And so what we're doing is not really anything different than the biotechnology that plants do today, but instead of plants using our current atmosphere, we're using an organism that was really the plant millions of years ago when our atmosphere could only sustain these types of organisms. And all we've really done is gone back to that time and picked an organism that was robust enough to do this chemistry. When I talk about this, sometimes it feels a little bit like science fiction, but it's not. We've got more than 40,000 combined hours at multiple sites, many steel mills throughout the world, and we're now in the process of commercializing our technology. We are building from this 100,000 gallon scale that I mentioned. We're going to commercial facilities at 3 steel mills, one in Europe at ArcelorMittal, the largest steel company in the world, one at China Steel in Taiwan, and one at Shougang Steel in Hebei province. The picture I had originally shown you was a steel mill that Shougang owned, which is where the first commercial facility will go. That will be a 15 million gallon a year facility, and we will also have one at China Steel in Taiwan and one in Ghent in Europe. That will be 20 million gallons. I hope by 2018 we'll have multiple commercial facilities operating. Now, at the end of the day, we're all doing this because we want to really have the environmental, economic, and social benefits that are required for us to move into that new world of a circular economy. What you're looking at on the left is life cycle data done by E4Tech showing a reduction of 70%, almost 80% of the carbon footprint when you start with a fossil gasoline versus taking a waste carbon from a steel mill and recycling it to make ethanol. The carbon footprint very much depends on where you are in the world, and so we've done multiple life cycle analysis, Michigan Tech in the U.S., the Roundtable of Sustainable Biomaterials in China, Tsinghua University in China, and Ecofis in Europe, showing that we get 50 to 70% carbon reduction relative to petroleum. This system is all based on water recycling, and of course, no land is used. There are no biodiversity issues. There is no food versus fuel or other such issues. But what we are doing is providing a revenue stream from a waste material, which we believe is really going to be the driver for utilization of waste materials. Because once you've got a business proposition, it actually becomes a pool of technology that can convert waste products. We also believe that these types of technologies, not just ours, will provide regional resources to produce energy and therefore This will provide energy security. And in addition, one of the most important things that happens when you have new technology, as you know, is that you create new jobs. Not only are these green jobs, but new technology creates jobs, period. As you know, when an industry is at its full capacity, their purpose is actually to reduce costs, to improve efficiency. And so they're always actually reducing costs, reducing jobs. So really most of the new jobs come from new industry during a build-out phase. So we believe that is an additional social benefit, not just a reduction of carbon and waste, but also the creation of new green jobs. One of the questions that I always ask is there enough waste gas streams for us to actually have a meaningful impact on the creation of a new fuel economy? And the answer is yes. If you look just at steel mill waste alone, globally, we could produce more than 30 billion gallons per year of ethanol. If you look at refineries, there are some gases in refineries we can use. And there we believe we could make over 5 billion gallons a year. We note that we can also impact PVC plants, ferroalloy plants, et cetera. And so this just gives you a sense, an order of magnitude of what is possible in terms of producing fuels and chemicals from waste. If you look on the next slide, one of the things we're trying to do as a company is actually create a company, not just create one production facility. And so using this gas fermentation platform, using this waste gas carbon recycling platform, we believe there's a variety of gas streams. I've already mentioned some manufacturing type like steel and PVC and refining, and I'll mention a couple of others. But then also we take the view that ethanol is just our first product, and that long term we want to be able to take these waste gases and also produce chemicals. In the next slide, one of the things I want to articulate is beyond manufacturing waste gases, we can also gasify municipal solid waste to make a gas that our organisms can eat and make into products. And so the view we have is that, as you know today, this is just the U.S. Municipal solid waste tonnage, 254 million tons per year, of which, as you know, we compost or recycle about 30 to 40% of that municipal solid waste. But the rest is actually in landfills and not usable. So there, what we're doing is we are combining with gasification partners, which basically can take that gas, that waste solid, and turn it into a gas that we can utilize. The goal being that we would get to a point where we have 100% of the municipal solid waste being recycled into products. If you look on the next slide, again, back to the building a platform, let me now not just focus on the gas inputs, but on the products. If you look today, one of the key raw materials in the chemical industry is ethylene. And ethylene today can either be made from fossil sources or it can be made from carbohydrates, whether it be sugar or corn. It can be used as ethanol, which can then be used to make ethylene. We can do exactly the same thing from waste gases. We can take the alcohol and dehydrate it to make ethylene, or oligomerize it to make butenes, or aromatize it using known technologies to make benzene, toluene, and xylene. And the reason these are key raw materials is because that's how plastic bag, toys, clothing, packaging, carpeting, these are the raw materials basically. This is the basic building block for most of today's chemical, what we call the petrochemical products. And we can make all of this as well from industrial gases. If you look on the next slide, just to give you a sense of the difference between making ethanol for fuel versus making ethanol for chemicals, the difference is that in a case where you are making a chemical like, say, a plastic wrapping, now all of a sudden your carbon emissions, your greenhouse gas emissions become negative. And the reason for that is when you take a waste gas and make that into a fuel, eventually that fuel, ethanol, is combusted. So it does eventually go back up into the atmosphere. If you instead make something like plastic wrapping or a plastic container of some sort, now you're essentially locking that carbon, call it a sequestration, but you're locking it into a chemical product, and there you fixed it as long as the life of that product exists. For plastic bottles, if we assume we're starting with ethylene, it's not negative because of the fact that not all of that plastic bottle would come from our technology and recycling carbon. But you can see you're still getting a reduction relative to starting with a fossil resource. So we're really excited about the concept of making chemicals, not just fuels, from recycling of carbon, because again, that is now a non-geological sequestration of the carbon. And really what we need to do is take more and more carbon out of the air. If you go on to the next slide, the other thing that we're also doing is converting ethanol. As you know, ethanol cannot be put into an airplane. You need to have a drop-in replacement jet fuel to put into an airplane. So what we can do is we can take the ethanol and oligomerize it, make it into larger diesel or jet fuel molecules. And we are working with HSBC, Virgin Atlantic, Boeing, to do that with technology that was developed under a DOE grant at Pacific Northwest National Lab. We're taking that technology, making jet fuel that we hope to put into a demonstration flight with Virgin Atlantic later this year. So we're really excited about this. And I like to say hopefully someday a steel mill will not just make the steel for the wing of a plane, but it will also, using its waste gases, make the jet fuel that goes into that wing. And that, to me, is really the paradigm shift of what we're trying to do here. And like I said, later this year or early next year, we will be doing that in an airplane and showing the world that you can think differently about both a steel mill and an airplane. If you look on the next slide, one of the things that, of course, the world always debates these days is the food versus fuel. And while I note that there are places in the world where food does not compete with fuel because there is enough land to produce both, most places that is not the case. So what I want to show you here is using a refinery waste gas and our gas fermentation technology, you can produce the ethanol, but in addition, we are producing also biomass. Our organism, as it grows and divides in our bioreactor, we actually extract some of it from the bioreactor because it's reproducing so quickly. So that bacteria that we're removing from our bioreactor is very protein rich and therefore can be used as animal food. It can be used as fish food. In addition, if you wanted to, instead of using it for animal food, you can use it for fertilizer. Now what we're doing is integrating a fermentation unit into an industrial site, no land use, no water use, and we are instead not just producing a fuel or a chemical, we are producing food or a resource to grow food. So this is really exciting, and I think it takes us from the food versus fuel debate to a food and fuel debate. In addition, because all of this growth of the bacteria is occurring inside a bioreactor, we are not only not using land, but we are also not irrigating the land. So now the food is being sourced at a very low water impact. And as you all know, the food, fuel, energy nexus is really all around the need for water. And so we believe, again, that using these approaches, we will be able to stay outside of that paradigm. Okay, you've seen this slide before. Again, it's what we're trying to do. I just want to spend a few minutes talking about the fact that ethanol and the ethanol value chain is not the only thing that we are trying to do. And so we are also trying to make other chemicals. The organism that I've talked about is a naturally occurring organism, as I mentioned, but we are also learning how to genetically modify it to make other chemicals like isopropyl alcohol, like butadiene, like succinic acid, all of which are critical in the production of things like nylon, and we are learning how to make some of these products from these waste gas streams. And the next slide is just to show you something which we believe is going to, again, disrupt the industry. If you think about market cycles based on fossil feedstocks, usually what happens is when butadiene prices go up, everybody wants to build butadiene capacity. This is true of thermocatalytic world, the world I used to live in, where catalysts are very much dependent on the reactor design to be able to operate. That is not true in biochemistry. In biochemistry, if you will, you can think about the reactor as your hardware, and you can think about the microbe as your software. And just like in the IT world, the hardware doesn't have to change every time you upgrade your software. This is also true in biotechnology. And to me, this is something that will have a huge impact in the chemical business, because what you can do is it takes 2 years to put in steel in the ground and build a hardware, build a production facility. But over time, if a market like butadiene market gets very high and valuable, you can switch your unit from ethanol production to butadiene or some other chemical production. And so now, instead of chasing a chemical market cycle, you can actually be prepared by just dropping another organism. And so all of a sudden, you're getting away from a world of commodities and how the commodities are viewed to a very different way of making fuels and chemicals. If you go to the next slide, we go back to how we think about carbon, and I've introduced you to a lot of concepts, but really what I want you to think about is that carbon cannot and should not be a one-way street to a dump or to some liability. Carbon, if we can start to recycle it, we can make both chemicals, we can make fuels, we can prevent the CO2 emissions, but we can also recycle some of the residuals that are in our municipal solid waste. So this is something that to me is extremely exciting, and that is creating a circular approach for carbon rather than a one-way street. And to me, that will allow us someday to recycle carbon into products and hopefully allow consumers the ability to choose a pair of yoga pants that comes from recycled carbon or that comes from, if you will, a fossil first-time use carbon. Quoting Michael Braungart, you know, there is no waste in nature. Every part is utilized, reutilized, and this is really how we should be thinking about manufacturing. This is really how we should be thinking about human consumption. What we do with our waste, I believe, is what will define us and what will define our ability to coexist with other folks, other people on the planet, as well as animals, and preserving our environment. And so I would ask all of you to rethink carbon, to rethink steel mills, and to really embrace the circular economy. And I hope someday that you can start with a steel mill that recycles steel to make cars and airplanes, steel for both of those. In fact, today, steel industry recycles almost 90% of their steel, but that with their emissions, with their gas emissions, we can take those and carbon capture and reuse them, CCU, into the fuel that goes into those cars, or carbon capture and sequester, but sequester not being a biological word, a geological world, but rather sequester into products, into chemicals, so that you're not only making the fuel that goes into the car and the steel that's in that car, but also all the other things that go into that car out of that waste carbon in a steel mill. To us, this is a carbon smart world, and this is what we are working towards. Thank you for taking the time to listen. Hello? Hello?
Hi, Jennifer. Can you hear us?
I can now, yes.
Okay. Thanks for that. I think I was still on mute. I just want to say thank you so much for that very, very interesting and insightful presentation. I certainly learned a lot about what you're doing, and very inspiring to hear your story. So we've had quite a large number of questions coming through, and if there's any further questions, I just remind the audience to please keep sending them through on the chat function to the host of the session, which is Quinton. So I'm not going to go in any particular order here, Jennifer, but if you're okay, I'll kick off into some of the questions.
Yes, absolutely.
Great. Okay, so the first question from the audience is a great one to start, I think. So one of our participants said that they think that the innovations that you're working on within your business is fantastic. However, does this change the fundamentals of the energy sector, and would it encourage the continued use of increasingly finite resources, in your opinion? Or will it help encourage the right use and the reduction of carbon?
And I'm not sure I fully understand the question in terms of continuing to use finite resources. And if the question is, will we still need to make steel and other such, I think the answer is yes. As I mentioned, steel industry already recycles more than 80% of the steel. The only reason there is growth is that recycling all of that steel isn't enough for all the steel that's required. I think that recycling the gases from the steel will help them on an economic basis, but it will drive ideas also that allow them to more effectively capture their wastes and use them for other products. In fact, I think that's actually the avenue that is opened up. So instead of thinking about recycling the product itself, not just in steel, but in every industry, not just recycling the product that they're trying to make, but starting to get people to think about recycling all of the other bits, their effluents, to make products that could then substitute. You know, for every ton of ethanol we make, 5 barrels of petroleum stay in the ground, right? So at the end of the day, that is really what we're trying to do. So I do think it encourages people to think about how to reduce waste and emissions rather than always utilizing our precious, fresh resources.
Great. That's a fantastic answer, and encouraging to hear that you think it will help enhance the positive and continue to reduce the negative impacts. So a second question from our audience. One of our participants has asked, they would be interested to understand what is the percentage of global carbon emissions which could be captured and transformed with the technology. So what's the maximum impact potential for carbon reduction?
Oh, that's a good question, and I don't think of it that way. I think about products that can be made from it. Well, let me actually, yeah, I can tell you. We looked at a steel mill, a typical steel mill, for example, and from a typical steel mill, we believe that doing something like this would be the equivalent of taking 20,000 cars off the road every year. So that would be a steel mill that is making about 15 to 20 million gallons of ethanol. So that would be the equivalent of taking 20,000 cars off the road. We've also calculated that if we used all of the waste gas from steel mills in China, if we could do that, that would be equivalent to taking 10 million cars off the road. So I don't have an actual carbon reduction number, but that is how we think about it in equivalence of automobiles. And just so you know, we don't only think about it in terms of greenhouse gas CO2 emissions, but also particulate emissions, because if you're not combusting carbon, you're also reducing particulate emissions, which of course are really important in the developing world.
Great, thank you, Jennifer. And another individual asked through the chat along the same lines, but a slightly different question. So they commented they think they need another explanation of how you can achieve negative carbon emissions through the recycling process. And they asked, could this mean that in the long run we could potentially not only minimize total emissions but achieve a net reduction in emissions below a baseline year?
That is only possible when you're making chemicals, because the carbon then gets locked into a chemical product. And so that is exactly the point, that hopefully we can start to take emissions and lock them into products. And instead of putting them in a hole in the ground as you would do with sequestration, I would add something that I think is really important. Please understand, we are only one technology. I really believe that this world of gas fermentation or gas utilization will really become a big deal in years to come. And so, yes, I do believe that more and more companies like us will be capturing carbon from the air, locking it into chemical products, not just fuels. And like I said, in a chemical product, then it's locked in. So someday, if all of the chemicals come from these waste gases, we could be getting towards a negative carbon emission.
Great, thanks so much, Jennifer. In a follow-on question to this from a different participant, they've asked, do you think that this could be rolled out on a large scale to developing economies? So how could you see that scaling?
Yeah, I actually think that the developing economies where, you know, there's a lot of these types of resources, whether they're economies where more and more they're reliant on manufacturing, and therefore there are these waste gases, but also waste biomass or waste municipal solid waste can be turned into products. So I do believe both in developing economies as well as the developed world, there is a huge opportunity to have a regional approach that does a carbon reduction and provides local jobs, local fuels, local chemicals.
Great, thank you so much. And an additional question that I think follows on from this as well. One of our attendees has asked, in the absence of any other price mechanism, i.e. carbon price, what is the break-even ethanol price point that makes your process viable?
In the absence of any, again, it very much depends on where it is, but if we're looking at a China case, I think if you're at $1.50 a gallon of ethanol, this will pay back in under 5 years, which is what most people are seeking. So $1.50 to $1.75, no support mechanism required.
Great, thank you so much. A new question that just came in right now from one of our audience members. They've asked, where could the technology be potentially applied besides steel mills? Is there a chance to tap into smaller sources of emissions, for example, vehicle exhaust?
Oh, that's a great question. And unfortunately, the answer is no. The process, I mean, maybe someday I won't discount that, but near term, these are units that require us to be able to have concentrated gases like 25% active gas for the organism to eat. And so it's hard for me to imagine that the very dilute gases out the tailpipe right now would be something I could process economically. Not with this technology, I'm sure with others, but not with ours right now.
Okay, thanks for that insight. So another chat question has come in. So they've listened to your response there and asked, how about in the agriculture industry where greenhouse gas emissions are a big issue? Do you see that being plausible?
Absolutely. I do see that possibility. In fact, we're working a project with Amentus in California where they are collecting waste biomass very close to one of their sites. So residue biomass in this California area, it's being gasified and then utilized for our process. I know also there's a lot of waste methane that is being collected, say biogas, from animal husbandry approaches, and there that biogas could be reformed and utilized for our process. So yes, you could imagine units within the agriculture sector, et cetera, yes.
Great, thank you for addressing that. And this question's from myself. So I attended a circular economy conference recently, and there was a lot of talk about legislation and whether it had a positive or negative impact on some emerging innovative circular companies. So what I'd like to ask is, do you feel that additional legislation in the geographies that you operate, would you like to see, do you think additional legislation is needed to support the work you're doing to help expand, or do you see it as a barrier or perhaps even has neutral impact on what you're doing?
I think legislation is a two-edged sword. Often legislation is not something I would call technology. Often legislation is based on what people see today. And so, for example, you look at legislation that defines biomass without having thought about the fact that a million years ago our bug was biomass. And so they limit biomass, for example, to plants and trees that they can see today. And so they question whether our bioethanol is truly bioethanol and does it qualify for the incentives that other bioethanol qualifies for. So here we are not only competing against an established fossil industry, but we're also competing against other biofuels. And that is very destructive for us because we can't compete against people that are getting these big incentives. However, when there's technology neutrality, like the low carbon fuel standard in California, where all they care about is what goes in and what goes out and how much carbon reduction you achieve, that legislation is very helpful because it incentivizes people to get better and better and better at reducing their carbon footprint in their process, right? Because then their incentives get bigger. But there, nobody's excluded. Anybody that can reduce carbon is part of the low carbon fuel standard and can qualify, and therefore we can all compete and let the market decide what the best technologies are. So I guess my view is I'd rather not have legislation than have legislation which is not technology neutral, because legislation that is not technology neutral creates significant barriers for new technologies. And I would also say that if we were to write legislation now, I would assume our technology would be included. But again, caution. What about the guys that are coming 5 years from now, 10 years from now that we haven't thought about? So if we're going to have legislation, let it be technology neutral, or let's just not have legislation, let us compete.
Yeah, great. Well, that's probably an insight we hear from others as well, so good to get your input there. So just a final couple questions to wrap things up. So we've talked quite a lot about the technologies and the potential within your business and within this innovation. So switching gears slightly, how much of an impact do you think the technology in your company can have on employment and what you might classify as circular or green jobs? So what's the human impact of this?
So the way we think about it is there's direct jobs during the construction phase, and those are in the hundreds per unit, per facility. And then after the unit is up and running, then you have the permanent jobs, which are on the order of 30 to 50 people operating the plant or doing things to support it. Of course, then there are thousands of indirect jobs that are created, but those are not the direct green jobs that you're talking about. So for the first 2 years during the construction, it's literally hundreds. But then after construction, it will be in the 30 to 50 permanent jobs.
Great, thanks so much, Jennifer. Good to hear about that side of things. And I guess one final question to sum it all up. Again, from my personal perspective, I've obviously through our Circulars program that we've run with the Young Global Leaders and the World Economic Forum, seen how you've managed to grow and continue to innovate over the past 2 to 3 years. So very interested to hear where do you see yourself taking the business and the technology and the innovation going forward, and what's the forward-looking trajectory?
Yeah, I use the old Roosevelt chicken in every pot. I'd love to see technologies like this, technology like ours, in every manufacturing facility in the world. I think there's a case to be made for capturing gases at almost every manufacturing site globally, not just steel, but like I said, PVC, refining, et cetera. And so I'd like to get to a point where we are making significant fractions of fuel. I like to talk about 20 to 30% of aviation fuel in the next 10 years, and also producing chemicals and really getting ourselves so that when you buy a bottle of some soft drink, that some of that bottle is from recycled gas, and I'd like to have that type of impact. I really hope someday people can choose at a grocery store where the carbon in their products comes from.
Great. Well, that's a very positive note to end on, and I hopefully we'll get there someday soon. So Jennifer, I'd just like to ask, is there any final comments or anything you'd like to add? We will wrap up in a minute or two, but is there anything final you'd like to share with the audience before we close?
The only thing I would like to share is just that I think that everything, we are trying to reduce carbon, and while I talk about steel mills and refineries, everything we do to conserve energy carbon impacts our ability to meet that 2-degree change, which is going to be so difficult to achieve. So think about everything you do. Unplug the bricks from the wall, turn off the lights, and then try to encourage new industries that can also help with all of this. That's it.
Great. Well, thank you so much for answering all those questions. There was a few more that came through, but I think we've asked you quite a number, so we'll leave it there. I'd just like to thank you very much, Jennifer, on behalf of the Accenture team, on behalf of the Circulars team, and behalf of Peter Lacey and the Young Global Leaders Circular Economy Task Force co-chairs for taking the time out today to speak to the group and share some insights and some very interesting facts about your organization and the work that you're doing. It's definitely a fantastic and inspiring organization, and we very much commend you for the work that you've been able to produce. So with that said, I will close the session. Thank you again for all those who participated. If there's others on the call who do have a interesting circular economy story to share, Jennifer would hopefully echo this, but we'd love to see you enter the Circulars Awards that the Young Global Leaders and the World Economic Forum puts on. So please do visit the website www.thecirculars.org and share your circular economy story with us, and you might see yourself presenting here next year as Jennifer is doing today. So thank you again, Jennifer, and for the participants on the call. We are available for follow-up. Please just send an email if there's any additional questions or comments. And do take a look in a couple of weeks or so at the website on the Circulars website, where we'll post up the presentation in case you missed any portions of the presentation. So thanks again, everyone, and have a good morning, afternoon,